Everybody, hope you had a good weekend. That first homework assignment, number 7, which is just some of the basics of open channel flow geometry, that one is due on Wednesday. And then the next submission you have is for the project. We'll talk a little bit about the project today. The phase 1, which is demand estimation, you need to upload to Blackboard by 1 o'clock on Monday, March 7th. So we'll talk about the project for a moment, but then after that we're going to get into chapter 11 in the book. We're going to be talking about steady uniform flow. Okay, so on the subject of the project, remember that demand estimation is effectively finding out what is the flow rate required at each of the green arrows on this map. Each of those green arrows you're trying to determine during the design condition how much water is going to be consumed. And we want to make sure that the pipes are big enough to satisfy all the demand for water in the network when this development is fully constructed and on the peak design condition, which may be the peak day plus fire conditions in some cases, and in other cases it's the peak hour. So the summary sheet that I've provided, this demand estimation summary table, I think is a good guide to what calculations you should perform. If you're trying to figure out how much water they're going to use in the north zone, it's related to the residential demands and the commercial demands. And of course, there's a handout I gave you that each student has different assumptions in terms of population density. And so if you measure the area in the north zone and you multiply that area by the given population density, then you're going to know how many people are in the north zone. And then what you need to do is figure out how much water is the average person going to use on the average day. And then there's the peaking factors. The peak day to the average day is at 1.8, I think 1.8, and then 3.25 of the average day to find the peak hour. And then there's this column peak day plus fire flow. And so the larger of the two, the larger of the peak hour or peak day plus fire will be the design flow for the residential demands. And you'll notice the commercial demands don't have any fire flows that need to be accounted for, and that's why that cell is left empty on the right side. It's just to let you know that it's the peak hour flow rate that is going to go into the design flow. So the design flow is peak hour commercial plus the larger of peak hour residential or peak day plus fire flow for residential. And then once you have the design flow for the north zone, if we go back to that map, you'll notice that the north zone has 2 green arrows that are feeding the water. So here at A, there's this interior green arrow that's feeding water into the north zone, and M is feeding water into the north zone. And so then back here to our demand estimation summary table, design flow rate per outlet, there's 2 outlets that's feeding water in the north zone. So it would be the design flow divided by 2.
What about the stadium?
The stadium is its own separate thing that is an external flow. So that's not, it's not inside the north zone. Yeah, so if we look at the map and take a look at the stadium, it's adjacent in the north zone, but it's not some of the interior demands. So the pipe that connects A and B, it's definitely going to have to account for the stadium. But as far as this demand estimation summary table, it's its own thing down here later on. So certain things have peaking factors that are applied, and we peak things that vary based on human use. You know, humans are inside the hotel in the middle of the night not using much water, in the evening using more. But look, the food processing plant just has 1 box there because it's not subject to the same peaking flows. You need to think about how much water are they using at the food processing plant. And the whole point of this is we want to make sure that the pipes are big enough for the worst case scenario. So let's say that your food processing plant used 40 million gallons per week. mg stands for million gallons. So if your food processing plant uses 40 million gallons per week, over what time is going to be both the worst case scenario and also likely? So a conservative assumption. So here, I'll tell you what a non-conservative assumption would be. The factory is open 24 hours a day, 7 days a week. And so they're using that 40 million gallons over a continuous time frame. That would be non-conservative because Q is volume per time. And so if I assume that the factory is always open, that's a lot of time for that quantity of water to be used. But it's possible that there's factories where they're only open 40 hours a week, right? And so it would be more conservative if we assume that the food processing plant is using its allocated water volume over the standard 40-hour work week. And then that would give you a higher flow rate, and you're going to make sure that the pipes are the right size so that you're able to deliver that full flow rate. So that's one of the cautions I'd give you. And you also need to think a little bit about irrigation of the golf course. In the past, students have said, well, let's see, I need to deliver, you know, if the depth that you have to apply to the golf course is ½ an inch, and then you multiply it by the area of the golf course, you're gonna find a certain volume. Some people have divided that volume of water by 24 hours a day times 3,600 seconds per hour. And so that's non-conservative, and also it would be a nuisance to the golfers. If you think about it, what they're suggesting is that the water is always on at the golf course. And so the pipes wouldn't be big enough to deliver the amount of water that's needed if the irrigation period is a shorter amount of time. So I'm not going to tell you how many hours you should irrigate. I'm going to let you reason through that. But what I will say is, don't assume that the sprinklers are always going at the golf course. That would be non-conservative and bad for the game. All right, I assume. I've never played golf, but
Yes, it would not be good.
okay, that's what I figured. Not good for the game. All right, so any questions before we move on from the discussion of demand estimation? You've got, what is it, a week? So your draft submission for demand estimation will be 7 days from now. Yes?
Do we assume a certain amount of commercial properties in the North Zone?
I think I assigned it on the basis of population density, similar kind of lines. Let's look at that again. Parameter assignments here. So North Zone commercial population density. So you're going to measure the area of the North Zone and then use the population density. Just think about people are in a commercial space. How many people in a commercial space? And so that's like people standing around at their job in the mall. That could be the consumers that are also there. It's kind of a blended, just how many people are in the North Zone during the design condition in commercial areas. Other questions? Let me think if I can give you some more tips. You know, this is the first year I've given the tip about the golf course. It was always interesting to see who would think through that you don't want to be irrigating all the time. It was about half and half usually. High density housing, that just means like an apartment complex where they're really cramming people together, like dorms. Dorms is high density housing. All right. If there are no other questions, then let's talk about steady uniform flow and normal depth. That's a loaded term, right? Normal depth. That presumes that any other depth besides the normal depth is somehow abnormal. Let's come back to this if we've got time, because we've got a few other examples, and so we'll come back to this trapezoidal channel geometry example if we've got the time. I want to jump straight into this discussion. This would be non-uniform or unsteady flow would cause this kind of a profile. So let's just see at what we're looking at. There's a horizontal elevation datum against which all of the depths and elevation datums are measured against. And then here's the bottom of the channel. See that cross-hatched pattern? That could mean anything from concrete to clay. It just means that this is solid, and above that is the water. So you see the triangle. That means it's a free surface of water that's open to the atmosphere, and these little lines are meant to invoke the thoughts of like a rippling water surface. Okay, so we've got water, and you can tell that the water is getting shallower in the direction of flow. By the way, what direction is the water flowing? Is it flowing to the right or to the left? Well, since this is open to the atmosphere, water can only flow downhill. In closed conduit pipe, water can flow uphill if it's an enclosed pipe because of pressure effects. But when it's open channel flow, water can flow uphill just for a brief moment. If it's got some momentum, like there are water parks where you'll be on the water slide and it goes uphill briefly, but not for very long. But let's just say that water is going from the left to the right, and you can see that it's getting shallower as you go downstream. So for us to predict what the water depth is when we have non-uniform flow like this is a pretty complicated process. We're going to learn the basics of it, and like the professionals who work in this field, for instance at the Army Corps of Engineers, they use software called HECRAS, which what you have to do is you have to break up the river into all these little pieces, and you do calculations on each piece to find out how the depth is getting shallower or deeper in the direction of flow. So it's complicated, and we will get there, but for normal depth, you'll notice that the water slope is parallel to the channel slope. Whereas in this prior slide here, the slope of the channel is different from the slope of the water, because you can see that the water is getting shallower as you move downstream. That means that the slopes can't be equal, that the water surface slope is steeper downhill, and that's why Y2, the depth downstream, is less than Y1, the depth upstream. So this is non-uniform flow. This is uniform flow. Uniform flow, just to refresh your memory from fluid mechanics, is that there's no change in depth or velocity in the direction of flow. So the characteristics of normal depth is that the slope of the channel bottom, S0, is equal to the slope of the water surface, SW, and then above the water surface is this imaginary line. Here it's abbreviated TEL to mean total energy line, and that's how our textbook this semester describes it. Last semester, our textbook would call that the energy grade line, EGL. But basically, it is some imaginary line that's above the water surface by a distance equal to the velocity head, v squared divided by 2g. All right, so when you have normal depth, you could calculate the magnitude of the shear stress that's being applied by the solid surface to the water. So the reason why the water is in equilibrium and it's not continuing to accelerate as it goes downhill is because a shear stress is applied by the solid surface to the water. It's not infinitely getting faster and faster and faster as the water goes downhill. There's friction. And so the friction is that if the water's moving to the right, the shear stress applied by the solid surface to the liquid is to the left. And so you can calculate that by knowing S sub F, the slope of the energy grade line. We've seen this formula before, and you'll apply it on problem 1116 in the homework, which is coming up. Not the immediate assignment you're working on, but it's coming up in the future. So the normal depth, why not, is not changing. You'll see here, why not is at location 1, why not is at location 2. Normal depth just means that the flow conditions are constant in the direction of flow. So the same thing wasn't true in this illustration. In this illustration, which was non-uniform flow, y2 and y1 are different. They're different because the water surface slope is not parallel to the channel bed slope. And so there's something downstream, like think about water flowing over a cliff that's drawing down the water here. There would be some feature disturbing the flow to cause this non-uniformity. Whereas in this illustration, we're far enough away from any kind of obstruction that it's achieved an equilibrium so that the flow depth isn't changing. Now, steady flow is when the conditions aren't changing with respect to time. Uniform is when they're not changing with respect to position, and both have to be true for us to see the normal depth, steady and uniform flow. So the equilibrium between the energy is that water is both picking up energy as it flows downhill, but it's also losing energy to the shear stress that's applied by the surface. And so the energy gain from a change of elevation is the same as the energy loss due to resistance. In the previous part of the course, we would have called that the energy loss due to pipe friction. Here it's not a pipe, it's just friction with the channel. So if you measure the head loss, H sub F, the head loss due to friction, that's the same as the delta Z for some increment. You know, for a certain length of distance between the upstream and downstream location, the energy loss is equal to the change of elevation if you have normal flow. It won't be equal when you have non-uniform flow. And so later on, when we have to get really sophisticated and complicated about things, what we'll do is we'll differentiate between the energy loss and the delta Z. But here they're equal. The slope of the water surface, the slope of the channel bed, and the slope of the energy grade line are all equal. All right. Mannings equation is used to characterize the effect of that shear stress. So the resistance to flow. My favorite, and your favorite, I hope, method of calculating resistance to flow when it was pipe flow was Darcy-Weisbach. And it's our favorite because it's so accurate. Maybe if you're thinking in terms of simplicity, then Hayes and Williams comes out on top, but it's not as accurate. Well, we don't have to choose. In open channel flow, we just effectively always go with Mannings equation. Mannings equation is the tool that we use, and in prior years they used the Chezy equation, which we've talked about before. There were these roughness coefficients C to describe the effect of shear stress, but more recently Manning showed that there would be a better fit between experimental data and prediction if instead of hydraulic radius to the 1/2 power, if we used hydraulic radius to the 2/3 power. So here's Manning's equation in terms of velocity. And I know previously I told you that all you have to do to get the flow rate from that velocity is V times A. So in other words, when we have Manning's equation, we'll commonly say it is the area to the 5/3 power, slope to the 1/2 power, divided by n times the wetted perimeter to the 2/3 power. So that will give us Q. This is just another representation of the same thing. Of course, as I've written it on the board, would be for SI units. If we have British gravitational units, then we have this conversion factor of 1.49. The n values are the same, regardless of whether you're working in British gravitational or SI units. Of course, here's a formula that we could use to convert between Chezy C values and Manning's N, depending on what data we've got, the surface characterized in. Here's some typical N values. The lower the N value, the more smooth the surface is. So there'll be less resistance for a low N value. A higher N value means that the water is going to have a lower velocity because there's more resistance. Okay, so what would be the flow capacity, Q, if we have a channel that is 1 by 3. So it's 1 meter by 3 meter. Let's say it's 3 meters wide and 1 meter of depth. What is going to be the flow rate if we have a 1% slope? Now in the Mannings equation, you can see it says put in the channel slope as a decimal. So that means that S is 0.01. It's described as smooth concrete. So concrete has a range, 0.011 to 0.02. And if the person finishing your concrete puts a lot of effort into making that smooth, then you may have a different end value than if you have a relatively rough finish on it, like if it was broomed with a coarse broom. For this, we're going to use the smooth side of things, 0.011. Because remember, the lower the end value, the higher velocity. Low end values correspond to smooth. Okay, so if it is an area of 3 square meters, because it's 3 by 1, and the wetted perimeter, P sub W, wetted perimeter is 1 plus 3 plus 1. It's just that perimeter that the water is in contact with. So it doesn't include where it's open at the top. That's not part of the wetted perimeter, where it's touching the air. We only want to include the location where the water's touching the resistance surface. So the wetted perimeter here is 5 meters. Why don't you pop that into Mannings equation, and let's find out what is the flow capacity, what flow rate, Q, in terms of cubic meters per second, could we expect for a 1% slope? Okay, so in part A, we're just trying to find out what's the capacity of this channel. We only want the water to be 1 meter deep. And it may be that the channel itself is deeper than that. If you look how I've sketched it out, I've got the edge walls go a bit higher. Maybe it's just that we want the water depth to only be 1 meter inside of this channel. So at a 1% slope, what Mannings equation suggests is that it would be 19.4 cubic meters per second. Now, here I've written the Mannings equation a little bit differently than I did on the whiteboard. But R, hydraulic radius, the definition of R is area divided by a wetted perimeter. So the reason why I think that this maybe is a little bit better is in this way that I've written it on the screen. We've got area, and then inside of this hydraulic radius is area and wetted perimeter. So I'm just combining together the area to the 3/3 power with the area that's embedded inside of this hydraulic radius. So it's the same formula. It's just that then we'll have wetted perimeter in the denominator to the 2/3 power. So 19.4 cubic meters per second is the capacity of this channel if we are going to have a depth of 1 meter, width of 3. Now the capacity would be higher or lower if this surface was made out of something else, because right now we're talking about smooth concrete. So if instead it was rubble, like broken up rocks that you'll sometimes see lining the edges of a channel, it would be a much lower flow rate. If we're dividing by the end value, then if you go from 0.11 for a smooth concrete to 0.022, then you're cutting your flow capacity in half. The second part of this example is asking, for a depth of 1, what channel width will convey a flow of 30 cubic meters per second? All right, so let me erase some of these calculations that are on the board right now. We're still using Mannings equation. For a depth of 1, and the slope stays the same, we're going to assume that this is still smooth concrete. It's just we don't know what is the width. So we're saying B is what, in order to achieve a Q of 30 cubic meters per second. All right. So here in our rectangular channel geometry, area will be B, the unknown width, times 1. That's the area. And the wetted perimeter, P, is, if we have this width and a depth of 1, it would be 2 plus B for the perimeter, because there's 1 on the left, 1 on the right, and then however wide the channel is. Okay, so we need to substitute into Mannings equation a flow rate of 30 cubic meters per second. And then for area, I'll substitute in basically B, because it's B times 1. So B to the 5/3. And then the slope is 0.01 to the 1/2 power. And then down here, the denominator of the right-hand side, we've got the n value, which we're sticking with, 0.01. And the perimeter is 2 plus B to the power of 2/3. All right, so do you have an equation solver on your calculator? Or I suppose you could set it up in Excel, where you're just playing around with different values of B until you get the right-hand side of the equation is equal to 30. These numerical methods are going to become increasingly important in this part of the course. So, being able to type in Mannings equation into your calculator and solve for some unknown parameter is really important. So I'll solve this using Excel, but I think it's probably even more important to be able to do it on your calculator. But just because I can bring Excel up on the screen, let me show you how you do it that way. So I've got some guess of B, like how wide to get 30. Well, we know it's going to be at least as wide as 3, right? Because 3 meter width gave us what flow rate? 19. So it's not a linear scaling, but it's going to be at least 3 meters wide. So I'll start with a guess of 3.1. That's my guess of B in meters. All right, and then here I'm going to type in the flow rate, the formula using my guess. So I'm just going to type in Mannings equation. So it's going to be this guess of B to the power of 5/3 times the slope to the 1/2 power, so 0.01 to the power of 0.5 divided by 0.011, because that's my n value, and then times, I'll put this in parentheses here, 2 plus B to the power of 2/3, so 0.66667. Okay, and all of that, close the parentheses around it because it's all in the denominator. So let's just check to make sure I've typed this in right, because I know that if the width is 3, then the flow rate's 19.4. So yeah, it looks like I've typed this in right. So what the problem is asking is, how wide does the channel need to be to get 30 cubic meters per second? So is it 3.5? No. 3.7? No. I can do goal seek because I know what the goal is. Data, what if analysis, goal seek. My goal is I want to know what width, I want the flow rate to be 30 by changing the width. Okay, so let it go. So this is saying 4.26 meters would be the width that gives me that 30 cubic meter per second flow rate. you could just put this formula in your calculator and it's effectively doing the same thing in the background. If you were just going to try to linearly extrapolate, like the width of 3 gave you a flow rate of 19.4, therefore what width would give you a flow rate of 30? If you assumed linearization could apply, then that would suggest that the width should be 4.64 meters, but that's not right. Because what happens is that when we make it wider, the ratio of area to wetted perimeter changes. So Manning's equation has to keep separate both of those things, the area and the wetted perimeter. And that's why the hydraulic radius is in Manning's equation. Any questions before we move on from this illustration? Okay, so here's Manning's equation. I may ask you to solve for any one of these variables. Now, I could say, like in part A, what's the flow rate for a channel of known width? You want to limit it to a certain depth. We know the slope of the channel and the roughness. Find Q. Or I could say, I know the flow rate I want to send through this channel, and I know what the geometry is going to look like. I know how deep I want it, how wide. So what slope is required to achieve that flow rate? So now you're solving for S. Or it could be even that you're solving for the roughness that's permissible for a certain flow rate you hope to accomplish. So that's why it's good to be able to type in Manning's equation into your calculator. And really, this example was pretty simple because we had rectangular geometry, but sometimes we have trapezoidal channels. And we'll work an example in a moment where that's what we're doing, is combining trapezoidal geometry with Manning's equation. Okay, so any examples before we move on from this example? Any questions before we move on from this one? So here's what our table 11.1 from the textbook says is the range of roughness values for different types of material. It's pretty tricky when you're an engineer and you're used to like really precise and repeatable quantitative approaches, when what you have to do is go out in the field and just look at a river, and maybe when it's dry would be the best time to see the bottom and say, well, let's see, it's some broken up rocks and a little bit of exposed earth, and you have to rely on engineering judgment to know exactly which N value to apply. It's not like when you're in the field, the N value is hovering above the river like a heads-up display or something. It's really just experience and iteration kind of calibrating, measuring the flow rate when you have a channel that you know what kind of materials it's made out of, and just gaining some experience and appreciation for what the characteristics are in your region. So these are the N values. You won't have to face that uncertainty in this class. I'll always just tell you the N value or give you a table to look it up, but I'm just letting you know that if you're going to do this kind of engineering in the real world, selecting the correct N value is sometimes the hardest part, is feeling really confident that you've got the right N value. One of the ways that you can feel a little bit more secure about it is that if it's a gravel lining, then there's a relationship between the diameter of the gravel grain and Manning's N. So this empirical relationship that if you know the grain diameter in feet, then you could determine the correct N value to use by this empirical equation. But as far as I know, there aren't too many expressions like this where you could go into the field and take a measurement of something and then from that know which N value is appropriate. I mean, you can with a concrete channel, but it's the natural channels where it gets a little bit tricky. Let's skip over this example. It's kind of simplistic and we're running low on time. I think that this is the more important example for us to try because it's a trapezoidal channel. Here is from table 10.1 the area, wetted perimeter, top width formulas for Mannings equation with a trapezoidal channel. So the bottom width here is lowercase b is 3.5. The depth of flow here is 1.2. And then if it has side slopes of 2.5 to 1, you'll notice that that is saying the horizontal is 2.5 and the vertical is 1. So that means T is 2.5 in this example. Okay, so we want to know what flow rate is going to be achieved here if we have smooth asphalt, 0.014, a bed slope of 0.1%, and a flow depth of 1.2. So let me erase the whiteboard here. Let's work through this one together. So trapezoidal channel where b, lowercase b, is 3.5. The depth y is 1.2 meters. The slope of the channel is 0.001. And our n value, 0.014. And T, so the way it works with these side slopes is it is 1 to T. Vertical is 1, T is the horizontal component. So T is 2.5 in these formulas. Okay, so Manning's equation says Q is area to the 5/3, slope to the 1/2, n times p to the 2/3. Okay, so we'll substitute in the known geometries here. The area, this is saying, is b plus ty times y. Okay, so b plus ty times y. Okay, so that area is to the 5/3. And then slope is to the 1/2, so that is 0.001 to the 1/2 power. N value is 0.014, and then the wetted perimeter, we have to calculate W. We'll do that separately somewhere. But then the wetted perimeter itself is going to be B plus 2YW. And that's to the 2/3 power. All right, so I'm going to pause for a second and allow you to, with the given B and Y, calculate what is the area with the given B, Y, and then you need to calculate separately W. So W is, in our case, 1 plus T squared, so it's going to be 1 plus 2.5 squared, and then all of that is to the 1/2 power. So find W, then with W you'll be able to find the wetted perimeter, but make the substitution for width, side slope, depth, and let's see if we can find out the flow capacity of this trapezoidal channel. So we can use these formulas for like area and wetted perimeter. Or sometimes you can just think of it this way. It's a rectangle, so area is 3.5 times 1.2. And so then it gives you, that's the rectangle area component of it. And then what's the area of the edges? So if we're going up 1.2 meters, and it's a 2 to 1, 2.5 to 1, then that means on each side, let's see, 1.2 times 2.5. That means that the length here is 3 and the length here is 3. So area is 3.5 times 1.2 plus 3 by 1.2. And then the wetted perimeter would be 3.5 plus 2 times the square root 2, because there's 1 on each side. Then we just find like the length of this. The length of that is the square root of 1.2 squared plus 3 squared. I just point that out because my solution didn't actually calculate W. I just went and said, well, it's a rectangle and 2 triangles which combine together is another rectangle, so we can find the area that way. So let me show you the solution I have for that one. So here you can see I'm saying that the top width is going to be lowercase b, the bottom width, plus the extra length that's on either side. So what I hope you found was that the flow rate is 14.96 cubic meters per second. Manning's equation only applies if you have steady uniform flow. Otherwise, things get tricky, and we can get tricky too, but just keep in mind that this is a really convenient formula, but it assumes that the flow conditions are steady with respect to flow. Okay, so just to summarize the announcements, you're working on this easy homework 7, which is due on Wednesday, and then you're working on the fun design project phase 1 submission, which is due on Monday. So you've got easy and fun. All right. See you next time.